students, welcome to the Electrical Engineering channel. In this lecture, I will start the new section of this course of DC machines, and the name of this section is DC motors. Previously, we discussed magnetic circuits. We also discussed DC generators. Now I will start the section of DC motors. And the definition of a DC motor is an electric motor is a machine that converts electrical energy to mechanical energy. And the principle of a motor is that when a current carrying conductor is placed in a magnetic field, it experiences a torque, and torque is also called mechanical force. Mechanical force exerted by the motor is equal to BIL. So here the requirements for producing a torque in a motor is the magnetic field or magnetic flux, the current carrying conductor, and L is the length of the conductor or length of the current carrying conductor. So B is the magnetic flux density, I is the current through the coil, L is the length of the conductor. So if all these three things are present, then the force will be exerted on the coil and we can observe the mechanical motion. The direction of force can be found by Fleming's left hand rule, and the Fleming's left hand rule states that if the forefinger is placed in the direction of magnetic field and the middle finger is pointed in the direction of current, then thumb will indicate the direction of the force which is exerted on the conductor, right? So here you can see we have the magnetic field from north pole to south pole, so it is from left to right direction. This is the current carrying conductor and the direction of current is upward over here and downward over here, right? So what will be the direction of rotation of this motor? So by applying this Fleming's left hand rule, we can point the forefinger in the direction of magnetic field. We can point the middle finger in the direction of the current. Then the direction of thumb will be into the paper over here. For this side, the direction of thumb will be into the paper, so that will be the direction of the rotation or direction of the force which is exerted at this side. Similarly, over here, the direction of force will be exerted out of the paper. So CD end or CD side of this coil will experience a force outward, right, out of the paper, and this side AB will experience a force into the paper. So as a result, the clockwise rotation of this coil will be observed. Okay. So back EMF is produced in DC motors. Okay. So when motor armature rotates, conductors also rotate and cut the flux. As a result, EMF is induced which opposes applied voltage. This EMF is called counter EMF or back EMF. So the reason behind the production of back EMF in DC motors is that when the coil of the motor is rotating inside the magnetic field, then simultaneously it is fulfilling the principle of the generator, right? So the principle of the generator is that when a coil is rotating in the presence of the magnetic field, EMF will be induced. And when a motor is running, the coil is rotating in the presence of the magnetic field. So EMF will be induced across the ends of the coil. And that EMF will be called as the back EMF, right? And this is the voltage formula of the DC motor. Here V is the applied voltage, EB is the back EMF, and IARA is the voltage drop across the armature winding. In DC generators, V was equal to E minus IARA. In DC motors, V is equal to E plus IARA. And IA can be evaluated by rearranging this equation, and that will be equal to V minus EB divided by RA. We can multiply this equation with IA, so VIA will be equal to EBIA plus IA square RA. And VIA is the electrical input to the armature. EBIA is the electrical equivalent of mechanical power developed in the armature. and Ia square Ra is the copper loss in the armature winding, right? So this is the electrical input to the armature, and this is the electrical equivalent of the mechanical power developed in the armature, and this is the armature copper loss. So condition for maximum power, PM, or the mechanical power developed, is equal to VIA minus IA square R, right? Because this expression is equal to the mechanical power, and we can differentiate this expression with respect to IA, and we can equate the result to zero, and then we can evaluate the condition for maximum mechanical power, right? So in order to evaluate the maxima of this expression, we can differentiate this equation with respect to IA and equate that equation to zero, and then we can get the condition for maximum mechanical power. So the maxima of this expression will be evaluated as IARA equal to V by 2. Okay. So V is equal to EB plus IARA, and IARA is equal to V by 2, right? So it means EB is equal to V by 2. So this is the condition for the maximum power developed by the motor. So mechanical power developed by the motor will be maximum when back EMF is equal to half the applied voltage. So this is the condition for maximum mechanical power. Now I will derive the expression for torque in the DC motor. And the definition of torque is T equal to F cross R. Torque is equal to the product of force and moment arm, right? So power is equal to T omega, and this is the mechanical power which is developed by the motor, and it is equal to the product of torque and the angular velocity. Suppose motor is running at n RPM, so in one revolution, angle rotated is equal to 2 pi. In n revolutions, angle rotated is equal to 2 pi n, and omega is equal to total angle divided by total time, because omega is the angular velocity which is defined as the rate of change of angular displacement. So it will be equal to 2 pi n divided by 60. So P is equal to T omega. So it will be equal to 2 pi n divided by 60 multiplied by T, and it is equal to 2 pi by 60 into Tn, or it is equal to Tn divided by 9.55. 9.55 is equal to 60 over 2 pi. Now armature torque PA is equal to TA multiplied by 2 pi n, and here n is taken in revolutions per second, or RPS, and PA is equal to EBIA. This is the mechanical power developed in the armature. So we can equate these two equations. So TA into 2 pi n is equal to EBIA, and EB will be equal to n phi z multiplied by P over A, and here n is in RPS. This is the same expression which we developed in our previous lecture. And now we can substitute this value of back EMF in this equation, and TA into 2 pi n will be equal to phi z and P over A multiplied by IA. So TA is equal to 1 over 2 pi phi z IA into P over A, and this n will be cancelled out with this n, and here 1 over 2 pi is equal to 0.159 phi ZIA into P over A. So TA can also be evaluated from this expression, and it will be equal to EBIA divided by 2 pi n, and here n is in RPS. If we have n in RPM, then we will use 2 by n divided by 60 over here, so that is TA, and it will be equal to 60 over 2 pi into EBIA over n, and that can be written as 9.55 EBIA over n. So all of these are expressions of the armature torque which is developed in the DC motor. And last is the shaft torque, and this is the torque which is available at the shaft, and this is also called the output torque. So for evaluating the shaft torque, we will consider the output power, and output power is equal to T shaft multiplied by 2 pi n. So T shaft will be equal to T out divided by 2 pi n, and here n is in RPS. And if we have n in RPM, then T shaft will be equal to 60 over 2 pi multiplied by T out over n. So that is all about our today's lecture. And in this lecture, we discussed the definition of DC motor, the principle of DC motor, and we discussed the back EMF, the condition for maximum mechanical power, and some expressions of the torque which is developed in the DC motor. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.